Good afternoon, ladies and gentlemen. It's very nice to be here in this ACI Fall Convention dealing with a very special topic of seawater concrete. What I'll be presenting is a project between our university, King Fahd University of Petroleum and Minerals in Rahman, and Saudi Aramco, a joint research project. It's a major research project started about 3 years ago on the performance investigation of GFRP reinforced concrete structure in industrial facilities. And a part of it is seawater, sea sand, and brine concrete. And the topic of my presentation today is the development of sustainable concrete mixes using the hypersaline Arabian Gulf seawater, mechanical properties and durability. So a lot of papers have been published, and as mentioned earlier this morning, about 500 till 2024. And most of them really doesn't address one of the things which we find it over here is a hypersaline seawater. So I'll be addressing this hypersaline seawater, which is important because the southern Arabian Gulf is really having a lot of salinity in the seawater. So that's the content. I'll just skip it. Actually, in the factor in construction area, and more than 24.8 billion is spent to combat a large amount of corrosion which is encountered, where the structures can really even collapse, bridges have collapsed in 20 years. And due to this high annual cost of repair, rehabilitation, maintenance, again. Okay, so hopefully we'll stick to this one. So what Saudi Aramco in a major initiative has really worked on utilization of the non-metallic GFRP bars in concrete structures, and as a result of this initiative, the largest seawater channel or floodwater mitigation channel, 21.3 kilometer long, was constructed in Saudi Arabia and Jazan with about 11 million meters of GFRP bars, which makes it the world's largest GFRP reinforced concrete structure. And then at KFUPM, we have been working on like research segments in this channel where we have put bars at different spacings and at different types to see how it is performing over long term, other than a lot of other research which was carried out at the university. But still, I mean, there was an issue for industrial facilities with the concern regarding the fire. So in this project, we did a full-scale fire test on slabs reinforced with GFRP bars, and all this effort really paved the way for utilization of seawater in concrete, which is really having no risk of corrosion. And in the Arabian Gulf region, in the southern part, you can see that there is a large number of power plants, and nuclear power plants is also proposed over there in that area. And large industrial facilities are upcoming in those areas. And this part of the southern Arabian Gulf, it's really very hypersaline because of lack of probably of rotation of water, circulation of water in the Arabian Gulf region towards Qatar. And if you look at the physical and chemical characteristics of seawater worldwide, then you can see that typically it is, for example, in Florida, chloride is only 18,750. In Japan, again 18,720. Sulfate about 2370. And down there you can see over here that in most of the typical seawater, the chloride is 20, or in Arabian Gulf it is really more saline, but towards the northern side it is about 24,000 ppm, this chloride, and in Red Sea it is 22,219. But when we come to our southern part of the Arabian Gulf, from where we collected our seawater and where we wanted to see the effect of this going on the higher side, you can see that the total dissolved solids is about 90,000 milligram per liter, which is quite greater than the normal value of 45,000 milligram per liter in the Gulf, which leads to high conductivity also. And the salinity in open ocean is generally about 31,000 to 38,000 milligram per liter, whereas the salinity obtained from the site at Al-Uqair is about 50,588. And the chloride content is almost like double, 40,683. So we thought that let's look at the effect of Fairy on the other extreme side of high saline seawater. What is the effect on the concrete? So not only that, we also took the sea sand from this area, and the sea sand, which is also very highly saline, most probably because of the high salinity of the seawater. And you can see that the sulfate in the normal sea sand, which was collected, or coastal sand we can call it, was 2,800 sulfate and 3,604 chloride, as compared to the dune sand, which you can see on the right, the Al-Dahana Desert, is about 300 and 200. So very high content of chloride and high content of sulfate in the beach sea sand, which was used in our research with Aramco. And the characterization of those sea sand also showed that salt deposit on the surface of sea sand particles were there. And these are mostly silica-dominant dune sand with traces of elements such as aluminum and magnesium. Then also the third part of the concrete which we did was ultra-high salinity brine. And the eastern region of the Saudi Arabia is dominated by brine accumulation over an area of over the yellow area, which you see over here on the right side, is all 1,500 kilometers square where brine is available. And these are characterized by the accumulation of salt and other minerals due to high evaporation rates and limited freshwater input. The salinity level in these brine are extremely high, and you can see that's over here as highlighted, 162,684. Very high salinity, 4 times that of the normal concrete. And on the right, you can see at many locations near the coastline of that region, you will see water coming up. You can collect that, and that is very highly saline brine. And in a large area, just you go a few inches down, you'll get this water. So concrete investigated was seawater concrete with hypersaline seawater, and also we use OPC and selected supplementary cementitious materials. And then the second concrete was seawater and sea sand concrete, and the third concrete was BRC, which is the brine concrete, which is also studied. But in this particular presentation, we'll deal with the detailed study conducted on the seawater concrete. These are the raw materials which are used, OPC, silica fume, their chemical composition, limestone powder, and also natural pozzolan, which is available in the western region of Saudi Arabia, and large quantity was also used in this particular work. After a lot of trials, more than 50 to 60 mixes, we finally converged to these 5 mixes of different type, which was concrete with OPC and potable water, NW, and then concrete with the OPC and seawater, replacing the potable water. Then we tried with other supplementary cementitious materials like natural pozzolan, 20%, replacing the cement, and using seawater, and then silica fume, 5%, replacing the OPC. Actually, it was later increased to 7.5% using seawater, and natural pozzolan plus silica fume plus limestone powder. These are the 5 concrete which we finally decided to go and carry out detailed investigation. And there you see the details of the mixes which was used. Typically, Saudi Aramco mix has 370 kilogram per meter cube of cement that was fixed, and water cement ratio was generally kept constant, 0.4. And other than that, we have the coarse aggregates, which are natural coarse aggregate, and dune sand was used in most of the formulations. Then a set of large number of tests were conducted, fresh properties of selected mixes, then hardened properties of those selected mixes, and then a detailed durability investigation was conducted, including rapid chloride permeability, drawing shrinkage, water absorption, water permeability, chloride diffusion, and sulfate resistance. Other than that, in order to ascertain the performance of this concrete in the GFR and the performance of GFRP bars in this concrete, we just embedded the GFRP bars in this concrete, and after a certain period of time, we took out those bars and evaluated the tensile strength, transverse shear strength, and interlaminar shear strength, and the bond strength of the GFRP bars in this concrete. So those are some of the pictures of the preparation of the samples. Then that's the GFRP bars embedded in concrete and kept for 3 to 6 months, and then we took it out and tested them, and measurement of shrinkage, and also long-term exposure of these concrete to acidic solution and to sulfate solution for at least 6 months. So, and those were the preparation of the samples for GFRP bars, which were tested in interlaminar shear and other shear. Thus, coming to the fresh properties of this seawater concrete, because as mentioned earlier by Professor Nani, that slump retention is a very important issue, so that was investigated for all the concrete mixes, and as you can see, there is a significant reduction in slump retention of the concrete mix as compared to the conventional mix. But however, addition of plasticizers helped in maintaining the acceptable slump through almost 90 minutes period. So that was that required a lot of trial and changes in the mixes. We then look at the initial and the final setting time, and the initial and final setting time obtained for all of the seawater concrete mixes were in compliance with the ACI limits, and the final setting time recorded for all the concrete mixes was close to the ACI specified limit of 300 minutes. Some of them were like 258.7 and 290.1. Coming to the compressive strength of the concrete, except for the natural pozzolana concrete, which behaves in a different manner because of the less reactivity of the natural pozzolana, all of the concrete mixtures has compressive strength of about at least 50 megapascal. And the compressive strength of silica fume concrete was significantly higher, measuring about 57 megapascal after 28 days of seawater curing. By the way, I forgot to mention that all of them were made of seawater and cured in seawater, collected from the same source. And after 28 days increase in the seawater concrete was 2 to 3 megapascal at 180 days. So there's no significant increase beyond 90 days in the compressive strength. Then with respect to the modulus of rupture, you can see that it was 7.8 for the normal control concrete, and for all other concrete mixes with seawater, it was slightly higher than the normal concrete mix. With the split tensile strength also, you can see that higher split tensile strength compared to the conventional mixture made with the potable water. And among these, the silica fume-based seawater concrete exhibited the highest splitting tensile strength in its specimen. Then moving on to chloride permeability, the concrete mixes with the silica fume demonstrated highly superior resistance to chloride permeability compared to other mixture. And in contrast to And the natural pozzolan concrete and control specimen prepared with seawater showed significantly higher values for chloride permeability. The drying shrinkage was measured automatically by embedded shrinkage strain gauges, and you can see that with the exception of the conventional mix made with potable water, all the seawater concrete mixes exhibited drying shrinkage exceeding 500 microstrain. But however, if you go to ACI C618, which permits a further allowance of about 0.03 micron for pozzolanic concrete, then still all the drying shrinkage which was measured was within that ASTM C618 limit. But it's clear that with the addition of seawater, highly saline, hypersaline seawater, the shrinkage has increased significantly. Coming to the water absorption, the seawater concrete specimen displays reduced absorption level compared to the conventional concrete, and with average values around 2.5% for the seawater concrete specimen compared to 4.25% for the conventional concrete made with the potable water. And water penetration also reduced significantly. Diffusion coefficient was measured and almost of a similar level, not a significant changes was seen in the diffusion coefficient. Then coming to the sulfate attack, that was the point where it disagrees with what Dr. Nani earlier showed in his slides. We saw that there was a very significant decrease in the strength, and the mass loss was high, together with the pictures, if you can see, of deterioration due to exposure of these concrete mixes in the seawater. And you can see that almost like, whereas the conventional concrete lost 4.4%, but it kept on increasing, and even the silica fume concrete showed a very, very high loss of strength and weight. And otherwise it is thought that silica fume based concrete will really not allow that to happen, but it happens with the silica fume concrete too, under the sulfate attack. Then on the GFRP bars which are tested in the seawater concrete mixes, we didn't see any significant changes in the transverse shear strength, interlaminar shear strength. Bond strength increased, which we can see a little bit as compared to the conventional concrete. The bond strength was higher. Some of the reasons are stated over there. The tensile strength was almost similar, and the elastic modulus was almost similar. I'll skip those SCMs which were done, and we could see the cracks really, the fracture surface in natural pozzolan, which resulted in the lower strength with the natural pozzolan. And I will not just skip those findings. So the seawater can reduce the environmental impact of concrete production by conserving the precious freshwater resources, which is very, very scarce in the Kingdom of Saudi Arabia. And once if we can use this, with the help of this, this committee, once it comes up and we can start using it, it will be really, a big move towards preserving the freshwater resources in all areas in the world where there is a scarcity of the fresh water, and the utilization of SCMs in seawater can further enhance the sustainability, and it reduces the carbon footprint for concrete production. The use of seawater will reduce the CO2 emissions also, and the concrete developed with seawater and SCM can exhibit improved fresh mechanical and durability properties, and these concrete could be potentially utilized for industrial and all other application and coastal structures in the coastal regions. I didn't present the other two parts which we have done, but just I could, because some part is not completed in that particular research, In the case of seawater and sea sand concrete, there is a significant reduction in the strength. And for the ultra high salinity brine concrete, we also managed to get almost like 45 plus strength in 90 days. So that also shows that with a very, very high salinity brine, you can still maintain to get a very high compressive strength. It was a very rough mix and tough mix, but it was good. So that's the team working, and thank you.